Okay, so this one is related with the organic chemistry reaction. To understand the reactivity, you first have to understand where the source of functional group functionality. So the only functional group in this compound here is this ketone group. And the functionality coming from the polarity of the molecule, and the electron is more electronegative, so the electrons are being pulled to the oxygen. So therefore, this is this carbon here, and let me kind of delete here, delete some of them. This functional group, and then now because of the electrons are being pulled this way, they develop what's called a partially positive charge. The partial positive charge is called the delta plus. I guess in the other side is to make it neutral, called delta minus. So this carbon is essentially partially positive. So they are essentially looking for something that is electron rich, right? So this is essentially partially positive. When you look at the sodium cyanide, and the cyanide NaCN, this easily dissociate. Sodium wants to be sodium plus. I guess so this one wants to be Cn minus. So this is a negative one with a lot of electrons. So this cyanide, which is if you're looking at the Cn minus, their Lewis structure is you have a 1, 2, 3, 4, 5, 1, 2, 3, nitrogen with 2. So this is their structure because of the one extra electron in addition to 4 on the carbon. So 4 more charges more localized in the nitrogen here, or the carbon here. So the way that people write is we have a triple bond with the lone pairs and the lone pairs, but the charge is being heavily populated on carbon side. And so this is what has been made from sodium cyanide. And the sodium cyanide, it looks like a missile. Okay, it looks like a little arrow. Looking for, this is like an arrow with a negative. They're looking for something positive, and they look, say, oh, there's a positive one. So they're gonna do the reaction with the center. So what's going to happen with this is, because this is a partially positive, and so then they are going to essentially look for this negative compound called nucleophile. We're going to form the bonding. So now what you're going to have is form this carbon here, and this carbon CN form a new bonding. So therefore, you have made CH3C with a CN attached on this side, and then now because of the electrons are being electrons are being pushed to carbon, this ketone became O minus, and eventually they became the protonated, and the rest of them stay the same, CH2, CH3. So by doing it, this is a nucleophilic substitution where the Cn minus ion attached to the partially positive carbon center, forming a new bonding. So that's really the key feature. And this the double bond of in the ketone became the single bond here. So this feature, they are forming a new bond, and this one becomes a O minus and an OH. So this is the answer for this one is E. Okay, so this is what we call the addition polymers are being found from the monomer shown from here. And this is actually what we call the vinyl chloride. You don't have to know the name. This is vinyl chloride eventually made it into what we call the PVC. The PVC pipes that we use in this household, and this is made how these polymers are being made. If you're looking at the structures, I can rewrite as CH2 double bond CH, and chlorine is attached to the carbon, to make sure. And you have one pi bonding, one sigma bonding. And in the polymerization, what's going to happen is this pi bonding becomes sigma bonding with neighboring monomers. Okay. So this is a nearby monomers. So then what is going to happen is CH2, you keep your sigma bonding, CH with the Cl, and that the new the pi bonding that you have will be used to form the bonding with your neighbors. Okay, neighbor monomer, which is a neighboring monomer. Once again, it's a CH2 CHCl, and then they're going to continue to do it. So if you understand this, the pi bond becomes sigma bonding. So this is what we call this repeating unit. So when people write it, okay, let me write a repeating unit, CH, and then this one is the neighboring bonding, but they are kind of repeated, so it's only half of them belongs to this. This is like, half, that's a half, and this is a really repeating bracket, right? This is a bracket you have to use to let them know. So if you look at that, and then there are n of them repeating. So if you're looking at it, this one is a double bond, this is no, 2 chlorine, double bond, no, and this is too many chlorine, and this is a right answer. Okay, so this is I guess toward a more deeper subject. When organic chemistry makes a compound, you need evidence, and you need to bring in some what is called instrumentation tool, a characterization tool that you can use to identify, and something particularly what we call the IR, infrared spectrum, is very powerful for identifying the functional group. Okay, and if you look at it here, there is a very broad peak on this around the 3,300 wave number, 1/centimeter, and that's typically what we call the OH group. Okay, this one representing the OH group, and then this one is if you draw the 3,000, and this is the wave number higher than 3,000 wave number, lower than 3,000 wave numbers. Sorry, actually they put it in. If you're looking at this, this is a higher wave number, and my term is wave number is, this is a symbol that I use. So this, so therefore this wave number is smaller than 3,000 wave number in here, and this is what we call is aliphatic CH2. CH vibration. Okay. So from here, I can see the OH vibration. One other very important one is the peak around 1700 or 1715, and this is a very signature of what we call the ketone peak. Okay, there's a many functional group that contains a ketone, and this one, and this ketone peak is very, very strong in IR. Okay, but now I'm looking at a 1700, which should be around here. Do I see any peaks? Is actually, I don't see any peak. So that means no ketone here, right? You see very small one is actually, this is because of the CO2. Okay, CO. Okay, that's just I guess is a little background noise from there, but this compound has no CO. Okay, so because of that, the answer for this one is alcohol. somebody might wonder, okay, alkane that cannot be carboxylic acid. Wait a minute, carboxylic acid has a OH group too. Yes, it does. It does should show up as around the broad peak shown around here. But however, this ketone, I don't see any peak around 1700 or 1715. So therefore, carboxylic acid is even out. Ketone is obviously out. There's no ketone peak. So therefore, the answer for this one is an alcohol. Okay, based on this broad peak, higher than 3000. Okay, so now the question is, which type of the compound is represented by this molecule shown up here? It looks very complicated, right? It looks like OH groups here. There's benzene-like aromatic groups here, amine and carboxylic acid. This is really different. And then if you're looking at this, the choices that you have, and this is almost like a natural compound that is more like the compound that is used in the biochemistry. And now looking at this, and this is what we call the amine, and this is what we call the acid. And actually biochemists come up with this name called amino acid, which is a basic building block. If you combine the amino acid, you will make this peptide. The peptide is a shorter form, and then essentially protein that we have made up our muscles and all these the enzymes, and this is all the use as an amino acid as a building block. So amino acid, in a way, let me rewrite it: NH2 COOH. You have an amino group and acid group, and then there's a carbon, and this one is attached to an R, and this is what we call the amino acid. In this case, your compound happen to have R is something with CH2 with phenol-like attachment. And this actually, the compound that we call this, if you're looking, if you're taking the biochemistry, you will see it's called the tyrosine. Okay, this is one of the essential amino acid made of our body. So the generic name for this one is amino acid. The answer is A.